Hello, my name is Lieutenant Colonel Jim Gifford, and I work at the Defense Threat Reduction Agency in the Research and Development Directorate. I lead a team that goes out to Department of Defense war games and supports nuclear play within those war games. Part of our job is to go out and raise the nuclear awareness for soldiers, sailors, airmen, and Marines, and what it would be like if a nuclear weapon were used on the battlefield, dispelling a lot of the myths and overestimation we see in Hollywood movies.
Well, that's great. That's just great, man. Now what are we supposed to do? Man, game over, man. It's game over. What are we gonna do now? What are we gonna do?
Maybe we could build a fire, sing a couple of songs, huh? Why don't we try that?
First off, let's talk about nuclear weapons and what happens when a nuclear weapon detonates. As you can see in the slide, we have an amazingly cool-looking fireball and mushroom cloud. This is what you will see typically after a nuclear detonation. And when that weapon detonates, 50% of the energy coming out of that weapon is blast effects, traditional explosive blasts and pressure waves that we see from traditional explosives. You also get 35% of the energy coming out as thermal energy. It's a pulse of infrared radiation that is extremely hot and moves at the speed of light. 15% comes out as nuclear radiation. This is gammas and neutrons, gamma ray radiation and neutron radiation. About 5% of that 15 comes out as prompt radiation immediately after the detonation. And the residual 10% stays as residual radiation that typically is known as fallout. There is a small sliver of radiation that comes out in what is known as electromagnetic pulse, or EMP. It's really between 0.1 to 0.5% of the weapon, but again, a very small percentage of the detonation energy. So just to kind of put this in perspective, we're going to look at the Hiroshima bomb that was dropped during World War II. Right? It was roughly 15 kilotons. And when we say kilotons throughout this presentation, that's talking the equivalent of thousands of tons of TNT or dynamite. So when that weapon detonated, 180 meters around that detonation point was the fireball, and everything inside of that was vaporized. The fireball is estimated to be about 100 million degrees Celsius. So it will turn anything, even soil, steel, to instantly to a vapor. About 1.1 meters out, in a radius, a spherical radius from the detonation location, you have heavy blast damage. So your buildings, concrete buildings, are going to be damaged, potentially demolished, definitely structurally unsound. About 1.2 kilometers out will be the prompt nuclear radiation, where people will likely get a fatal dose and die within a month or so. And out to about 1.9 kilometers is that thermal radiation, that thermal pulse, can ignite most anything out at that distance, as well as cause third-degree burns on exposed skin of personnel in the open. So that kind of gives you an idea of what we're talking about here in this briefing. Now, we will not be talking about the megaton or very large nuclear weapons. We're going to be looking at what we can typically call a low-yield nuclear weapon, closer to 100 kilotons or less. Now, first we're going to look at some interesting testing videos. This first video comes from the Operation Teapot Shot B, and it was done in 1955, March 22nd. This is an 8 kiloton blast, and the height of burst was about 150 meters. So when you watch this video, notice you will see the fireball forming. It's almost instantaneous, and then you'll see it expand out. And if you watch very closely, you'll notice the fireball never contacts the ground because the pressure wave coming out bounces off the ground, keeps the fireball from touching the ground. That means this was a fallout-free height of burst. All right, so go ahead and watch this video. All right, so in that video, you noticed that if you saw the fireball did not contact the ground, but after the fireball went away and the mushroom cloud formed, it wasn't really obvious, unless you were kind of watching in slow motion, that the fireball never contacted the ground. So most low-yield weapons will be functioning near the ground, so it'll be hard to tell at the time of burst, did it cause fallout or not. And we'll talk about fallout shortly. All right, we have another video to show you. Now this video is a larger weapon at 29 kilotons, so almost twice the yield of what we dropped in Hiroshima. All right, again, height of burst around 150 meters. Now the camera for this blast is set up about 1.4 kilometers from the detonation, and you'll see when the video starts, you'll see a very bright flash of light, which is indicative of a nuclear detonation, and the weapon will be actually functioning off to the left of the camera. Now as soon as the dazzle or flash blindness from the bright flash goes away, you'll see some telephone poles, all right, or power lines, and you'll notice very quickly how they look to puff like smoke. Now that's the actual outer edge facing the blast of the varnish and just dirt on the side of that telephone pole becoming a vapor from that thermal pulse, and you'll see it kind of expand, and then as you watch, you'll see the pressure wave come by a little while later, kind of push all those cloud-like telephone poles to the side, and then you can eventually see about 3 seconds or so later the blast wave moving along the ground to the camera location and shake the camera. So the point of this video, when you watch it, is you can see that the thermal pulse, along with the radiation, the prompt radiation you can't see, is instantaneous because it moves at the speed of light. Whereas the pressure wave that comes out is a sound wave, much like lightning versus thunder, right? You're going to have that sound wave come a little bit while later, so you actually have time to get cover if you're far enough away from the blast wave, but that thermal pulse is instantaneous. So now I'll watch this video. All right, so hopefully you were able to see that. The timing of the thermal and the blast wave, we'll kind of talk about that as we go through each of these effects individually. So first we're going to start with the thermal effect. This is the one that's going to hit you immediately and will be the one you can kind of see, if you will, when it happens. So again, the thermal energy travels at the speed of light because it is an electromagnetic wave or a light wave in the infrared spectrum. For a 10 kiloton burst, it's about a second-long pulse. Larger weapons, about 100 kilotons, it's about 3 seconds. Now, when a thermal pulse hits you or hits a person, you can have skin burns. So we're talking first degree, second degree, or third degree burns. You have things set on fire. You also have flash blindness or dazzle. Now that's kind of what you saw in that last video, and it was very bright for a second, and it took about a second before you could actually see again. And that's what flash blindness actually is. The best way I like to equate it is if you remember back if you went to the movies in the middle of the day, you walked out around 2 o'clock after a lunchtime movie from dark theater, you walk outside on a bright sunny day and your eyes are kind of bright and you kind of, it's really bright. That's exactly what flash blindness is like, just dialed up, to 11, if you will. All right, and then finally you can get retinal burns. Now this is if you're looking directly at the blast when it happens. So when that weapon detonates, you're looking directly in that area. You'll actually get a portion of your vision that you will never get back because it will burn your retina. Likely you will not be completely blind. It'll be more like if you were a kid and you ever stared at the sun for a few seconds and you got that sunspot that went away after about a minute or so. Just imagine that never going away. So it'll be a portion of your vision that you will never get back. And just to show kind of how bright this can really be, this is a picture back from some testing back in the 50s, an above ground test out in the Nevada test site from the old Vegas Strip. Now you can see it's not what we would consider Vegas these days, but you can see what looks like a sunrise off in the distance. Now this was actually taken at night. This was a nuclear test done at night, and that is actually the nuclear detonation going off over 60 miles away. And that's how bright this energy is that comes off this nuclear weapon. We have another image here of just some personnel watching the test of a nuclear weapon, again, off at a very safe distance, but you can see how bright that detonation actually is. So if a nuclear weapon were to go off, right, in a future conflict, we would know it was a nuclear weapon just by the flash of light if you were in the near vicinity. So we have another video here to watch. This is a really cool old testing video of a house that's hit by the thermal blast and then the air blast. So when you watch, you'll see, it'll show it twice, you'll see the house, and again, the weapon is detonating off to the left side of the house. You'll see the front of the house will almost vaporize, and that's the paint on the outside being vaporized by that thermal pulse. But the side and the back of the house are actually just fine, and nothing happens to those from the thermal pulse. And what this is showing is the thermal pulse is just like, almost you can imagine shining a flashlight. So anything that's not in the shadows will be thermally burned. Anything in the shadows will be just fine. Then the cool part at the end of the video, you'll see the blast wave come and totally destroy the house. So let's watch. All right, so in that video, you saw, again, the house, the front side thermally vaporized, right? The outside, the paint, the outside layer, and then the rest of the house was fine until the blast wave came and hit it. So again, that just shows that thermal effects are line of sight, if you will. So what that means is if you are near a blast, if you are shielded or protected, not in the line of sight, you will likely have limited thermal effects against you. So that means if you're in a vehicle, you're in a building, you're in a foxhole. It turns out the ground is one of the best shielding things for all the nuclear effects. You'll likely be okay. That includes being in a forest, right? If you're on the other side of a forest, the trees will keep you in the shadows, if you will, from the nuclear blast, and you'll probably be okay. However, glass, so if you're in an office building, glass will not stop the thermal radiation, and you will still get burns. So you'll notice on the right I have a graph here of your distance from ground zero and the thermal fluence that you receive. Now, if you didn't know this, when you get your Ph.D. in a science field, they do require that anytime you brief an audience, you always have graphs and figures, or you lose your Ph.D. So in order to keep my Ph.D., I wanted to point this out here, that what we're showing in this graph, the green curve that kind of drops down really quickly is for a 0.1 kiloton, right, or 100-ton nuclear detonation, and the yellow curve is for a 10 kiloton detonation, so 100 times larger in yield. And you'll see there I have listed the values of thermal fluence that you get for third, second, and first degree burns. And I'll just point this out here by drawing some lines, all right, on the slide of where you get third degree burns for a 0.1 kiloton and a 10 kiloton. And you'll notice that while I made my yield 100 times larger, I did not go out 100 times further for my damage. It's a little less than 10 times, all right? So what that's showing you, and all of these effects, I'll have a graph similar to this, just to point out that nuclear weapons effects don't scale linearly with the yield. So that means I can't multiply my yield 100 times bigger and get 100 times more damage, right? The damage doesn't work that way, all right? It doesn't go out nearly that far. All right, I will point out that for the flash blindness or the dazzle that I mentioned earlier and the retinal burns, it's much worse at night than at day, during the day, and you can see that there for 10 kilotons for both those effects. And that's just because it's a stark contrast, right, of being daytime and then it's brighter versus very dark at night, and then a very bright flash of light can actually have effects further out. All right, so that's the thermal effects. Now we're going to move on to the other instantaneous or near instantaneous effect, prompt radiation. All right, so this is all the radiation, typically gamma ray radiation, and neutron radiation received within the first minute of detonation near ground zero. Like the thermal effect, you can have this reduced by shielding. However, you need a thick, very dense material like a metal vehicle, a very thickly armored metal vehicle, thick concrete walls, or a foxhole. Again, the Earth is a great shielding mechanism for all the nuclear effects. As you see there, your JSO suit or your MOP suit does not provide any meaningful protection from radiation. It will go right through that. So you do need a dense, very heavy armored vehicle to reduce the radiation that you will receive. You'll see I've got another of my graphs over here again of the 0.1 kilotons in green, the 10 kilotons in yellow, and you'll see again it's not 100 times more in the range for that immediate incapacitation at 1,000 gray, right? Or, sorry, 1,000 centigrade. And one of the key things with, unlike the thermal radiation, that you will know immediately that, oh wow, it's really hot, I am in the thermal radiation zone. For the prompt radiation, this gamma ray radiation, you won't know right away unless you are basically right under the bomb and you're getting an extremely lethal dose, much more than 1,000 centigrades. You won't know right away. And really the only way to know that you were exposed to radiation before you start exhibiting the symptoms is if you have a radiation meter on that is detecting that you were exposed. After the fact, it's really hard to figure out how much were you exposed to until you start exhibiting the symptoms. And then at that point, it's still hard to get a good estimation of what you had. So it's very important in an event where you think you might face a nuclear detonation that you have your dose meters, your radiation meters on and working before the blast happens. So what we're going to talk about real quick is what happens if you are exposed to this lethal dose of radiation or potential lethal dose of radiation. So this figure on the right is taken from an old Cold War doctrine, ATP 4-02.83, and it shows the percentage of lethality based on your dose if you have no medical intervention. And if you look at that graph, you see the 50% lethality on the left or the y-axis and trace it across. You're going to see that it crosses the curve roughly between 410 and about 450. All right, and what that means is if you get a dose of 410 or 450 centigrade, right? And it's a wide curve there due to the different effects on people that are maybe not as in good of shape, right? They're going to be closer to 410 children versus a really good in shape soldier is going to be closer to that 450 on the right. What that's saying is if you get exposed to that much radiation, you could die. 50% of people will die if they have no medical intervention. Now we can help reduce the effects of radiation and potentially save your life around 410, 450, even 500. But once we start getting closer to 800 and above, there's really nothing we can do at that point medically to undo the radiation effects. So if you are exposed to this large amount of radiation, you will get what's called acute radiation syndrome. And it's really noticeable by 3 phases. So you'll have your initial phase when the radiation first hits you in your body. It will manifest by being nauseous, vomiting. You'll be very tired. Right? Kind of sounds like some other things that could happen to you, maybe not necessarily radiation, right? Just getting the flu. Could be any of those things, right? Then your body's going to recover from those initial symptoms. It's going to fight those and get past the nausea and the vomiting. And you'll have that latent phase where you think you've recovered. Oh, it wasn't that bad. I'll be okay. However, the damage is already done, and just the permanent fatal damage takes a little while to manifest, and that is usually happens a little while later, depending on your dose. It could be a day later if you get an extremely high dose, or weeks later if you get just above that 410 or right around that 410. And what happens is the radiation will destroy your bone marrow, which means you can no longer produce white blood cells or red blood cells, so you're unable to fight off infection. That's why you can die without medical intervention. We can give you we can do some things to treat the nausea. We can also give you antibiotics to help fight off infection. However, if you get a really bad dose, your intestines can actually start leaking, as will your blood vessels, and you'll die that way at a very painful death. So just to kind of give you an idea, if you've seen the Chernobyl miniseries, it was on HBO, back in 2019, really good miniseries. You see the firefighters, they go respond to the exposed reactor that exploded. They are in the presence of exposed uranium, getting a very lethal dose without knowing it. You notice they don't immediately die. They're actually still fighting the fire for hours. And it's hours later they start getting sick, start getting that nausea and vomiting. They take them to the hospital. Once they take them to the hospital, they seem to recover. The guy's wife comes and visits him. They're playing cards. She's like, oh, great, he's going to be okay. They haven't really told them that it was radiation that they're going to die from. And then later on, a day or so later, the guy dies a very painful death, maybe a little over dramatized here with like his eyes not working and things like that. But that's kind of what happens. So you get exposed, you don't know it, you get sick, you go recover, you think you're fine, and then you die. Right, so that's why it's important to have that radiation meter, so you know, oh wow, I got a really high dose. I need to start antibiotics right away and see what we can do before it's too late. So when you do get exposed to radiation, it's not just the amount of radiation you get exposed to, but it's how quickly you get that dose. All right? So it's amount of radiation and the time you receive that dose. So most of our doctrine back from the Cold War uses the centigrade, right? It's little c, big G, little y. You can see there on the slides. That is the SI unit of measuring radiation. It's equal. A centigrade is equal to a rad, if you've heard that before. But there's lots of ways to measure radiation. So you might see it measured other ways in other places. But in Army doctrine, in fact, all DoD doctrine uses the centigrade. But if you get a small dose of radiation, your body can recover given enough time. In fact, we're all constantly being exposed to radiation from cosmic rays and radon in the ground. But it's a small dose, and our body has time to recover, so no one's going to die from those kinds of exposures. All right? But if you get exposed and you don't die and you don't get a fatal dose, but then you get exposed the next day or a couple days later, your body hasn't had time to recover, and that will accumulate and you get an extra dose of radiation. So the way that we track radiation in the Department of Defense is we use something called a RES category, which stands for Radiation Exposure Status. Now this all comes back from Cold War doctrine, all right? And you can see there there's 3 RES categories. There's RES 1, RES 2, and then RES 3 I've kind of split up a little bit more just to kind of delineate what you're going to see based on that exposure. So 1 to 74 centigrade is considered RES category 1. And you can see by doctrine we say that you have mild effects within a day. So within 24 hours, you're going to be a little nauseous, probably not even going to vomit. You're going to have no long-term effects. You're going to be just fine. Now once you get above 75 to 124, the light blue category there, that's RES category 2, you're going to have slight illness within a day. So instead of mild effects, you're getting illness, so you are probably going to vomit 12 to 24 hours later. You're going to vomit, have diarrhea, just feel terrible. You're going to want to be on limited duty because you're not going to feel like going out and walking a couple miles, all right, or doing your normal soldier tasks, all right? And you notice here it says no further exposure permitted. Now if you notice, look back down at RES category 1, it doesn't say no further exposure permitted. So it's okay if you get less than 74 to get another small dose, right? It wasn't until you get above 75 that the DoD says, hey, we should really keep you from getting any further exposure. All right, now once we move to a RES category 3, we're going to start in the yellow category there, 125 to 299. So you're going to get your illness and your weakness within a day. So we're looking at definitely within 24 hours, probably closer to 12 to 18 hours. And you see there it says 5 to 10% premature death. Now that's just cancer. So that means you will get cancer down the road. 5 to 10% of the people will, less than 300 centigrade. But the remainder will recover, and again, no further exposure permitted. Now we move up to the orange category, right? Still RES category 3. That's 300 to 529. All right. Now this is illness and weakness within half a day. So in 6 to 12 hours, you are going to have that vomiting, you're going to have that diarrhea, you're going to have that nausea, you're going to have that malaise. Now you're going to see the chance of cancer is going to increase up to 50% now. All right. And again, the remainder will recover. And again, no further exposure because it will just add on to that and bump you up to higher and higher categories. Now once we move to the red, it's red because that's bad, right? 530 to 799 is is incapacitation within an hour. So this is really close to you're going to be down, you're not going to be able to do anything. You will be combat ineffective, you see that there in red, right? Within the hour. So 30 minutes to an hour, you're going to be dropping, you're not going to be able to hold your weapon and fight, you're done for, all right? You are sick, and you see 5 to 90% of people will die within 4 to 6 weeks, right? We're no longer looking at cancer percentage, we're looking at your death down the road within 4 to 6 weeks, and it's going to be a very painful death. Now, once we get to 800 to 1,000, and then it's just even worse above 1,000, all right? It's black. That's immediate incapacitation. You're going to drop immediately. You're going to know, even though you can't see it, that you are exposed to a very lethal dose of radiation. They're going to be combat ineffective again. You're just going to drop on the ground. And 95% of people will die within 2 to 3 weeks, and there's really nothing we can do at that point, except try to make it a little less painful as your body deals with that radiation. Now, just to kind of give you an idea, most people are very unfamiliar with radiation, and how does this matter? What is 1? What is 74? How does that matter? So we're going to look at just some events and kind of convert these into centigrades for what you've been exposed to normally in your life for radiation, right? So if you get a chest X-ray, if you go to the doctor, that's about 0.01 centigrades. That's a very small amount. You can see there in the U.S., the average annual radon exposure is 0.228, so like 0.3 centigrades, right? We haven't even got to 1 yet. You got to get a whole body CT scan to get to a centigrade. And by OSHA standards, right, nuclear workers are only allowed to get 5 centigrades of radiation per year. Once they hit that max of 5, they have to stop so their body has time to recover so that they don't ever get to a point where they're going to get cancer. Now you notice 5 is what we say, hey, a radiation worker that works around stuff all of his life shouldn't get more than 5. That's starting to get dangerous. You notice for the military, right, we say up to 74. That's still res category 1. We don't even say no further exposure permitted, right? If possible, you wouldn't ever want to get exposed, right? But by doctrine and risk categories, we don't even say that because we're looking at, an immediate combat mission. Right, so we're looking the res categories are really to help commanders determine the risk of further exposure to their troops to continue the fight because, hey, we've got to keep fighting if these are used on the battlefield. All right, so you notice we have a little higher tolerance for radiation, and really the reason it was 75 is because 75, to make that jump from res category 1 to res category 2, back in the 50s and 60s, 75 was the first point from a blood test that we would see your white blood cell count drop enough to know that you were exposed, because if we didn't have a detector to notice that you were exposed. So that's why it's 75. All right, so moving on. That's radiation, all right? Just kind of the invisible killer of the nuclear blast, if you will. All right, so now we're going to move to blast. This is the one that is pretty common for those of us in the military, right? So we're going to get a blast pressure wave, right? So you're going to get both overpressure, which causes structural collapse, damages your organs, pops your eardrums, right? If you get enough, it could rupture your lungs. All right, and we're also going to get a dynamic pressure, that blast wave moving out, that's going to do translational effects or really strong wind. That's going to cause shrapnel, that's going to pick things up and throw them across the room. So not only could your lungs be crushed, but your body could be picked up, thrown against the wall. Another way you could die. This also, the dynamic pressure is what rolls over vehicles. All right, so I'm going to show a video here of the explosion from 2020 of Beirut. I think pretty familiar in a lot of our minds still. Now, I want to point out, you see there in red, this is not a nuclear detonation, right? Not a nuclear detonation. This is ammonium nitrate, which is a fertilizer that is used, you can make an explosive, all right? But it's been estimated to be somewhere around a kiloton. You see between 0.5 and 1.5 just because we're kind of scientists and we have error bars on things. But it's about a kiloton. So this is the best example of, in a modern city, what would a kiloton size detonation do and what would it look like, right? Obviously this doesn't have the thermal, this doesn't have the radiation effects, right? But it does have the blast effects. Now, just to kind of phrase this before we watch the video, this is roughly estimated about 2,700 tons, all right, of ammonium nitrate that exploded. That's an entire warehouse, all right, which is a volume of about 4,000, a little over 4,000 cubic meters, all right, of ammonium nitrate. This is a lot of stuff, all right? So we're going to go ahead and watch the video now. All right, so in that video you saw it was smoking and then it blasted and then you saw kind of just the pressure wave move. It looked like a cloud that's just vaporized, and it's actually causing the condensation of water vapor as it moves out, like making clouds. But you could see it kind of expanding out, and then unfortunately the guy recording this video, it kind of knocked him over, right? And he was pretty far away from that, but still the blast wave does travel pretty far out. But you had time to watch it, right? Again, the blast wave moves, it's a sound wave, so it moves through the air. It's a compression wave, so unlike a light wave, right, you have time to see it coming potentially and get cover. Like, I probably should have gotten down, but he wanted to record it, which is kind of glad because it was kind of a cool video. So if we move on, we're looking at some pictures here of the aftermath of this explosion. Right, so the large picture on the left, you can see looking down of where the detonation happened, you can see a crater there. That crater is about 120 meters in diameter, about 43 meters deep. kind of true, about the same as what you would see after a nuclear detonation. But you'll notice that everything near that detonation is pretty much destroyed, right? Even the silos that were right there, I don't think they're usable, but they didn't completely collapse. And you see a lot of the steel-framed, right, thinly steel-framed warehouses that were nearby, and the containers are all, demolished. But the rest of the city, right, a little ways out, kind of you see that like bridge almost a little bit in the distance, and then the rest of the city is still there and still fine. Even some of the like 3-story buildings behind the grain silos are still standing. All right, so if a detonation were to go off of this size, about a kiloton or so, right, in a city, you're not going to destroy the entire city. You're only going to damage a small portion of that city, all right? And again, as the blast wave moves out and hits the other buildings, those buildings are going to absorb a lot of that energy and reduce it even further. So if you can kind of compare this back to images of Hiroshima and Nagasaki, those cities were completely leveled, whereas here it's not that bad, all right? And that's partly because those cities back in World War II era Japan were mostly wood frame buildings, not steel reinforced concrete, right? So they were much easier to destroy. And if you actually look back at images from Hiroshima and Nagasaki, you'll see the few concrete buildings that were made are still standing while the rest of the wood frame buildings are destroyed near ground zero. Now if you look on the top picture, you can see that's the before picture, and you can see the warehouse that detonated, and then if you look, that's the second one kind of on that little pier sticking out, and then if you look down at the bottom right, you can see the looking down the aerial view, again you can see the damage really close by, but then the rest of the city is fine. Now you're going to have a lot of broken glass further out in the city, but the structures are going to be just fine. Now just again to frame that, again that was roughly 2,700 tons of ammonium nitrate that detonated, about 4,000, a little over 4,000 cubic meters in volume. That's a lot of stuff. Now, just doing the math as a nuclear engineer for the critical mass of uranium in order to cause a detonation, right? Just pure uranium-235, we're not talking about an actual nuclear weapon, just pure uranium-235, it's about 105 pounds to go nuclear. All right, for pure plutonium-239, it's only 22 pounds. Right, so if you imagine an entire warehouse of ammonium nitrate does this, all right, with pure uranium, that's about, I think, roughly the size of a volleyball or a basketball, about 105 pounds. And then for pure plutonium-239, it's 22 pounds, I think it's roughly about the size of a softball. So that's just the destructive power of these nuclear weapons. A lot tied up in this, inside the nucleus, right, a lot of energy. All right, so again, we've got another, my favorite plots here, right, showing you, again, comparing a 0.1 kiloton to a 10 kiloton, and you notice how quickly the air blast drops off, and the effects don't go nearly as far as they do with our light, or our electromagnetic effects of thermal and the prompt radiation. What you can see there, kind of the table I have in the top right, it compares a 1 kiloton to a 10 kiloton to a megaton. And you notice going from a 1 kiloton, 0.5 is approximate distance for looking at concrete building damage, right? 0.5 kilometers out to a megaton, it's 5 kilometers. So that's 1,000 times larger yield. I only get a 10 times larger effect in distance, right? And really it's because for blast waves, it's 1 over the yield to the third power. So it's not, again, not making my yield, doubling my yield doesn't double my damage, or 1,000 times my yield doesn't make my damage go 1,000 times further out. All right, so now we're going to watch a testing video, right? So back in the 50s, when we were testing nuclear weapons, right, we actually had soldiers go out. We would test a low-yield nuclear weapon, right, from an artillery shell. We would shoot it off in the distance, had the soldiers in foxholes at safe distances. The detonation would go off, and it would be a fallout-free height of burst. There was no fallout. They would then exit their foxholes and walk forward to ground zero, and they had staged some tanks and vehicles and dummies and uniforms so that the soldiers would see what it would look like after a blast and what they would expect to see flipped over tanks and dummies on fire and uniforms. Kind of give them that idea of, wow, this is pretty devastating close by, but I wasn't that far away and I was just fine. All right, helping them reduce the psychological impacts of seeing the aftermath of a nuclear detonation. So we'll go ahead and watch this video. All right, so in that video, you saw the soldiers in the foxholes. You actually saw the blast wave. They were pretty far out, so not enough to really cause any damage. But you saw the blast wave move over. You might have noticed, I think it's the third set of foxholes they show. You've got that really smart NCO there with his goggles on, and then a bunch of officers or privates not with their goggles on. It's pretty funny. But then you saw the soldiers just the blast wave goes over and they just jump up and walk forward like no big deal, right? That's why we used to do that kind of testing, just to kind of show the that it wasn't such a big deal after this nuclear weapon goes off. And it's not just game over, man, and we're all dead and the atmosphere's on fire and, we just give up. No, we got to keep fighting through, right? That's what's important about understanding nuclear weapons is these lower yield are not going to kill everyone and you can continue your mission anyways. All right, so looking at the casualties, kind of what we've talked about, the three main effects, right? The blast, the thermal radiation, and the prompt radiation, right? Those are all different ways you can die, and they kind of overlap each other. So if you're close to that weapon, you're not going to die one way. You're going to die multiple ways. Now, we haven't talked about fallout yet. That's next, right? But what I do want to show is, again, back to ATP 4-02.83. This is the predicted distribution of injuries you would experience from a nuclear detonation. So you can see most of the injuries are going to be in that bottom section, that combined injury section. And when you see wounds, that's the air blast, that's the shrapnel coming from air blast. But you can see there that 40% of the people are going to be damaged. Most of the casualties are going to come from radiation and burns. Now, just to kind of go back to Hiroshima, right? We talked about this at the very beginning, those distances. You'll see that going the furthest out is the thermal radiation, all right? And then the prompt radiation is the second furthest reaching one, right, at 1.2 kilometers. Right? So what that means is I'm going to get irradiated, not be able to fight infections, and I'm going to get third-degree burns, which burns all of the skin, right, all layers of my skin, and I need a skin graft to fix that. That won't heal on its own. And, oh, by the way, one of the worst problems with burn injuries, right, and that's why hospitals have special burn units, right, is because of the risk of infection. So not only am I risk of infection because I've burned my skin, but now I can't fight off that infection because the radiation has killed my blood cells, right, my white blood cells. So that's why we've got to start thinking not only about what are the effects could they do, but also what kind of injuries could I expect and what kind of capabilities do I need to have to be able to respond to those kinds of casualties. All right, so now we're going to move on to fallout, my favorite part. This is actually what I got my Ph.D. in, fallout. All right, so if the fireball, right, touches the ground, so it actually is close enough to the ground. We saw that first video, it didn't touch the ground, but if it were to touch the ground, right, the soil, anything else, buildings, tanks, whatever, people, they will be vaporized, immediately turned into a gas. All right, and they'll pull it into that fireball and they mix around with everything in the fireball. Again, this lasts for about 2 seconds after detonation, right, the fireball does, before it's cooled. And again, it's about 100 million degrees Celsius, so close to like the center of the sun. All right, so the vaporized soil mixes with what we call the radioactive fission products. Right, so these are all the things that come out of splitting the uranium or the plutonium. When I split those two atoms, I get smaller atoms out that are radioactive. Right, we call those the fission products. All right, so these radioactive atoms will mix with that vaporized soil, for instance. All right, and as that soil begins to condense, turn back into solid soil, like dirt particles, after about 2 to 3 seconds. All right, if it's mixed with that radioactive fission product, I now have a radioactive piece of dirt. And as that dirt gets bigger and bigger in the cloud and gets to a larger and larger particle, eventually gravity is going to win and it's going to get pulled out of the cloud, out of that, if you think about any detonation you've ever seen, you get a lot of dust, right, coming out. Eventually that dust falls to the ground. It's called fallout because it falls out of the sky when gravity wins, right? So we get a lot of the heavier, more radioactive products are closer to ground zero, and the lighter particles will blow further downwind and deposit downwind. Typically the fallout is all deposited within about 2.5 hours, depending on the wind speed, all right? And we have that fallout just on the ground, radioactive dirt, that is then irradiating you and causing a problem. Now, if we jump back to that video I showed earlier, right, where we had no fallout, what happens to those radioactive fission products? They don't fall because they stay as individual atoms floating in the sky. And they just continue to float and they spread out, all right, and they remain in the atmosphere. So a lot of our testing that we did above ground that was fallout free, fallout safe, right, those radioactive fission products remained in the atmosphere. They decayed away to stable elements and are still in the atmosphere to this day. Now, just to point out, for both Hiroshima and Nagasaki, we knew about fallout, and we didn't want to have that longer-term radiation on the ground, so we actually targeted our weapons at a fallout-free height of burst, or a fallout-safe height of burst, meaning we made sure that the weapon detonated at a distance higher off the ground than the fireball would be, so the fireball did not contact the ground and cause any fallout. So at both of those locations, people were able to move right back in within a day or two, right? Once the fires had been put out, they were able to move back in without any radiation concerns. Now, fallout is not a long-term issue for the military. You notice issue for the military is in red there, because for the military, for military operations, fallout is not a long-term issue like a lot of people think, right? Common misconception is that fallout makes the downwind area uninhabitable for many, many years, hundreds of years, right? A lot of people always think back to the accident in Chernobyl, right? That still has an exclusion zone of 35 kilometers around Chernobyl, and people aren't supposed to be there, right? Not supposed to live there, right? And it was such a huge thing, right? Well, there's a little bit of a difference between what happened in Chernobyl, what happens to a nuclear weapon, right? So just to kind of give you why that is, right? In Chernobyl, it was 192 tons of uranium that was exposed when the reactor exploded. Right, a nuclear weapon, we talked about this earlier. If I'm looking at just by the math, pure uranium-235, that is 105 pounds to go critical, right, and have a nuclear detonation. So 192 tons exposed in Chernobyl, that's a lot. 105 pounds out of a nuclear bomb, not that much, right? So the amount of stuff released that was dangerous is much higher in Chernobyl. And also, Chernobyl wasn't all a nuclear bomb that fissions instantly, right, or within nanoseconds, all right? And it's just my decay products. In Chernobyl, we still have uranium that's out there that's exposed. In fact, they took off like the top 3 meters of dirt to try to capture all that uranium that was exposed, but there is still some. So that's why Chernobyl is still a problem versus a nuclear weapon that's really not that big, as big of a deal for the military. All right? And in fact, most of those radioactive fission products, or those atoms that come out of splitting the uranium or plutonium, have very short half-lives and decay away relatively quickly. All right? In fact, for less than 100 kilotons, or in fact 100 kilotons and less, all right, most of the radioactivity for the military risk is gone within 2 days. All right? So why can I say this, right? Again, nuclear engineer, got to do a little bit of science, all right? If you look here, this is one of over 200 possible reactions when I split uranium. It's kind of a random thing that happens, all right? But when I split the uranium, the green circle there, right, uranium-235, you see that uranium has a half-life, or half of it decays away every 700 million years. So it takes a long time to decay away. It just stays there, constantly being dangerous, all right? Now you see the yellow box there. Typically, we say that after about 10 half-lives, we cut everything in half, and then in half, and then in half, and then half, and in half, right? 10 times, it's mostly gone. You can assume that it's decayed away, all right? So that would take 7 billion years to get rid of uranium. That's a long time. But when I split it, you see that in the bottom there, the orange decay chain, right, it goes strontium, yttrium, and then zirconium, right? That is 75 seconds for the first one, the strontium-94 there. 75-second half-life. So in 12 minutes, it's all decayed away to the next thing. To the yttrium, which is 19 minutes. So in 3 hours, it's all decayed away, and then it's stable. Right? So then it's not an issue anymore. Same thing when we go to the xenon, right? We go through 14 seconds, 64 seconds. That's why I'm saying these relatively decay away pretty quickly. All right? You see the barium-140 is about 13 days. That takes 4 months to go through 10 half-lives. All right? So that's a while. So that could be an issue. All right? And then the lanthanum is about 40 hours. That's about half a month before it's gone. But then I'm stable. So you can see these decay away relatively quickly. All right, and again, I'm taking my uranium and I'm splitting it. It's not necessarily going down this path. There's over 200 possible options, some of them have much faster decay chains. So what does this all mean? So here I have a representative plot of a fallout field that you would see after a detonation. You see the top graph there, the little plus sign kind of on the left, that is the target location. All right, and you can see I have these just generic ovals that kind of represent what it would look like if I had a wind blowing from west to east, right, blowing to the east. So the fallout's being blown to the east. And you can see there we have the blue oval is for 25 centigrade. It's kind of the limit for the civilian first responders, what their maximum exposure can be before they have to get pulled out. The green is 75 centigrade. Again, that's res category 1 for the military, right? Below 75, right? We're good, all right? Yellow is the combat emergency risk up to 125, right? That's the max we're supposed to go before we say don't get any more radiation, all right? And then red is that 410 where you first get that chance of getting a lethal dose, right? So that top graph there, what that's showing is if I were to be outside in the open, this is for a 10 kiloton detonation, if I am outside in the open, exposed, have no shielding, all right, the detonation goes off, I stand in place for 2 full days. What would be my total dose that I would receive? Didn't move, based on my location from ground zero. You can see the fallout plume goes out to beyond 50 kilometers. It's about 50 kilometers long, right, and about a little less than 10 kilometers wide. North and south there. So you can see you do have some risk. That looks pretty bad. But if you kind of look down at the bottom left graph, that is 12 hours, showing up 12 hours after detonation. So the bomb goes off, 12 hours later I show up, and I stand in place out in the open for 8 hours. Now that graph all fits in the black box up on the top graph. Right, so it's shrunk considerably if I'm only there for 8 hours, right? You see I have just about a kilometer long red there in the bottom left, from left to right, a kilometer and a little like less than half a kilometer north and south. All right, so really at that point you can see, wow, that's not that bad, and that's standing in place for 8 hours out in the open. So if I'm in a vehicle, that's going to go down because I'm not going to be as exposed. And again, this is all exposure to the dirt on the ground that's irradiating me, or on anything that's around. Right, just the dirt will settle on any flat surface basically. All right, now if you move to the middle graph on the bottom, you see that's showing up 24 hours after detonation. Again, standing for 8 hours, right? You notice there's no more red, there's no more lethal risk after 24 hours. That's, again, if I stay there for longer than 8 hours, I might start getting that. But typically if a detonation has gone off, unless it was, on something I need to go recover, like a base or something, I need to get the equipment out of there, right? If it's just out in the middle of the battlefield, I can walk, what is that, less than 10 kilometers, 9 kilometers long? I can walk 9 kilometers in 8 hours. Right, if I was walking east to west for some reason, but I could just walk around it, right? And then if you look at the far right graph, that's 2 days later after detonation. Again, staying for 8 hours. You see it's shrunk so small. There's hardly anything other than the blue, right? The yellow, right? The combat risk is tiny, right? So what that's showing you is that fallout for the military, for military operations, right, where I'm not standing in place for a long time, the fallout goes away very, very quickly. Now, if I want to go live back right next to that, say it blew up near my house, and I wanted to go move back in, right, within a kilometer of my house, that's going to be a long time before I get to a point where I can, by safety reasons and OSHA standards, I could say I could go back and live there. That'd be years before I go back and say I'm not going to get radiation that could potentially cause me cancer over the time of my lifetime, right? If I'm living there forever. So I probably wouldn't want to move back there, but if I'm doing military operations, I can get in and get out very easily. And you can see how quickly that shrinks, a slight tactical pause, and then it's safe to cross. It's really not like I'm going to do fallout and make an area uninhabitable for years or unusable. And if you have a radiation detector, right, with your unit, you can easily turn that on, and as you get close to the fallout, they'll start pinging you and let you know you've got some radiation, and you can just move around, right? All right. So that's fallout, right? Not as bad as you probably thought it was, right? Not the post-apocalyptic future that we always see in movies. Now, finally, I'm going to talk about the electromagnetic pulse, or EMP. Right, this is one that people oftentimes have a lot of questions about, all right, because we see all this stuff in Hollywood, right, and think it's so terrible and we're going to get sent back to the Stone Age. Probably not. All right, so how does EMP work? So first off, we're going to look at what we call a high altitude EMP, right, where we have a blast greater than 20 kilometers in the atmosphere. All right, so when I have a weapon go off up in space, I get an EMP on the ground. And really that works from two things. We call it E1 and E3. So first we're going to talk about E1 because this is the one that matters to military units. All right? When high energy gamma rays, I got a cool little image here to help you out. So when a burst goes off 20 kilometers or greater in space, all right, the gamma rays travel in all directions, but some of them move back towards the Earth, and they're going to hit atoms in the air and knock off electrons off those air molecules. Now these electrons get knocked off based on this high energy gamma at near the speed of light. And if they're up in the atmosphere, we have the Earth's magnetic field acting. And if you remember anything from high school physics, right, it's like charged particles. I was a chemistry major in high school or in college, so it's either right hand rule or left hand rule, but charged particles on a curved surface, on a magnetic field will curve, right? So that's what we're trying to show here is these charged electrons moving at near the speed of light will spin because of the Earth's magnetic field, causing them to produce synchrotron radiation, basically a giant pulse of electricity down, well, actually in all directions, but some of it's directed down to the Earth's surface there. You can see in the red arrow. All right. Now, why does it have to be between 20 and 40 kilometers there? Well, that's the Goldilocks zone, if you will, of air density. Greater than 40 kilometers, there's really not any air molecules, so the gamma rays just travel through the vacuum of space until they hit something between 20 to 40. Below 20 kilometers, air is too dense, and as those electrons are knocked off, before they can start spinning, they're typically absorbed by other air molecules, and they kind of quenches the E1 field from happening, or the E1 pulse from happening. So that's why the sweet spot is kind of 20 to 40 kilometers there. Now this pulse lasts for less than a second. It's faster than a lightning bolt, and this will cause damage potentially to your electronic equipment. All right. Now the other pulse that comes out that's often discussed when you talk about EMP, or if you go look this up on the internet or something, you're going to see something about E3. Okay. Now E3, got another image for you here. This is after the detonation happens. Is that those fission products and the hot fireball, right? Heat rises, so it's going to rise through whatever little bit of air there is, and as it rises through the Earth's magnetic field, those charged particles that are those fission products, they're charged. They're actually going to cause the Earth's magnetic field to distort, which I'm trying to show there with the blue lines in the image. And that distortion actually induces electric fields in long, straight conductors, things that are a kilometer or longer, like power lines. So it can build up charge in those power lines, which they can move down the power line and short out a transformer, knock out civilian power companies, or power issues, all right? Not really an issue for the military because we don't have anything that's a long, straight kilometer or more of a conductor, right? None of our equipment is that big or that long. So really E3 is more of a civilian issue, whereas E1 is what we worry about in the military. You might be asking yourself, what about E2? Well, E2 is just like a lightning pulse. It's all of our, it's kind of similar to E1, but not as bad, and it's slow enough that our normal like surge protectors will protect against that, and it doesn't cause a problem. So typically it's just E1 and E3. So now that we understand what EMP is, we're going to look a little bit about it. All right, so it's really not a factor for near surface bursts, and why we see that is that, we talked about high altitude EMP, right? Now if we talk about near the surface, so anything close to the ground where we're going to have any of those effects we've already discussed, all right, we get something called source region EMP, all right? Now it will affect equipment near ground zero and near where the blast goes off. That's what GZ stands for on the slide there, ground zero. But it's all within a kilometer, and the real strong fields are all going to be very close to ground zero, well within all of the other effects we've already talked about, well within that thermal, well within that prompt radiation, and within that blast. So likely if your radios have issues, you're also going to be, thermally irradiated, and you're going to have blast effects. So EMP is going to be kind of your last worry in that case. All right? But it can cause problems to electronics, circuits, microelectronics, things like that. So if you follow the EMP mil standards for hardness, right, that should get around those effects, right? You put your things in Faraday cages, turn off some of your equipment. It has to be powered on to have an EMP, all right? But really what we're trying to talk about here with EMP is it's not a definite effect. EMP is a very stochastic or random effect when it happens. So sometimes your radios will get a disruption, which is just like tripping the circuit breaker. They will power off. All you got to do is turn them back on. They'll boot up. They'll work just fine, right? It won't actually damage them. You get some damage, all right? But again, it's stochastic. It's not always the same every time. Right? And one of the things with the disruption, right, is your radio might get disrupted. That's easy. I turn it off, I turn it on, it reboots, everything's fine. But what could happen is I might have a network of systems all connected, and I have to go through each system. As I turn on my radio works, something's still wrong, and then I go to the next thing. Maybe it's this switch. Nope, that works. Oh, maybe it's this router. Oh, here was the problem. So it might take a while to determine what actually caused the problem, what actually was disrupted as I turn things on and off and power cycle them. And then it might be, that thing is disrupted, it might turn back on, or it might be damaged and I have to replace it. So if you're, in a chance of having an EMP, right, it's very important to have your critical equipment backed up or with spares that are powered off so that you have a replacement if you have an EMP effect. Now, if we jump back to high altitude EMP, right, that high altitude EMP detonation, that altitude of 20 kilometers or greater, can have an effect over a large area because it's kind of line of sight from up in space where that EMP effect goes. So just kind of to illustrate this, back in 1962, the last atmospheric test we did was a Starfish Prime test. It was actually 1.44 megatons, and they set it off 400 kilometers above the Earth's surface, out in the Pacific, right out kind of over nothing. It actually was about 900 miles away from Hawaii. Now, when the weapon detonated, about 900 miles away on Hawaii, right in the middle of the night, about 300 streetlights got knocked out. All right, and some burglar alarms went off. Now, think back to the 60s, right? We didn't have a lot of microelectronics, things that would have had EMP effects, so it could have been worse if they were to do that today, right? But it wasn't like, we didn't knock out all power and everything, right? It was just a small amount. So if you've ever seen Ocean's 11 and they do the EMP to knock out power in the Vegas Strip, right? That's a little overestimated, right? Thanks, Hollywood, you always do that to us. All right. Now, I do have a picture if you're kind of wondering, like, what would it look like? So this is actually from Hawaii, looking at that detonation. This is the middle of the night. That looks like the sun is up right through the clouds. 900 miles away, 400 kilometers up. That's what a nuclear blast would look like out in space. Right? Now, kind of, made sense to EMP things back when we didn't have a lot of satellites, but now that we have a whole lot of satellites in space, there's other things we have to worry about if we're trying to do that high altitude EMP. What about the effects to things in space and satellites? Right? So really I'm kind of representing 4 of the effects that could happen if you do a nuclear weapons detonation out in space. The first is just prompt radiation effects. So that is any satellites within line of sight of that detonation, right? We get gamma rays, we get the thermal pulse, we also get potentially some fragmentation from the casing of the device itself, right, the nuclear weapon itself, that can travel out and hit those satellites. Now, the gamma rays can actually hit the satellite and induce software glitches, turn a single 0 to a 1 in the binary code of that satellite, causing it to stop working correctly, right? It can cause power failure, mess up the solar panels. All right. We also have something called system-generated EMP, which is represented by the little lightning bolt at number 2 there on the bottom right satellite. All right. So SGIMP, as we like to use the acronym, all right, is when the radiation, right, from the gamma radiation from the blast hits a satellite, right, just like it knocked off electrons in the air, right, in the atmosphere, it can actually knock off electrons on the surface of that satellite. Now, those satellites are made of metal, typically, so they're good conductors. So those electrons will all kind of move around the surface of the satellite and collect, build up a charge, which then can travel inside the satellite and short out parts of the satellite, causing disruption or loss of the satellite, which could be a problem. Right now, besides the immediate effects, right, the direct line of sight effects, we also have a couple of delayed effects. First is belt pumping, represented by my radioactive green cloud there, right? So when my weapon detonates, I still get those fission products. They're not going to become fallout because they're not mixing with the ground, because it was at a fallout-free height of burst, definitely up in space, right? But those fallout fission products, not fallout, but the fission products are still charged particles, so they are affected by the Earth's magnetic field. They kind of get trapped there in the Earth's magnetic field as they decay away over time. Now, if we do this close to the Earth's surface, right, we have a lot of satellites in like low Earth orbit, or like the International Space Station, for instance, is in low Earth orbit, and it orbits the Earth roughly every 90 minutes. It goes around the Earth. So if it travels every 90 minutes through that cloud of radioactive fission product, every 90 minutes, the astronauts are getting dosed with all that fallout right there every time they go through. So they're getting exposed to a high amount of radiation every 90 minutes. Same thing with the satellites as they traverse through that area. Most satellites have some kind of radiation hardness for cosmic radiation, being out in space and not having the atmosphere to protect them. Maybe they have a 5-year life, for instance, of time for radiation exposure before they will fail. If they're continually every 90 minutes going through that belt of radioactive fission products, right, that time might go from 5 years down to 6 months because they're getting way more radiation than they're supposed to. So that's going to affect a lot of satellites. And again, you can't just target just enemy satellites or just, an adversary satellite. You're hitting any satellite that goes through that orbit. So you're going to cause a lot of damage to a lot of satellites doing that. And at the same time, you're also going to disrupt comms from the ground up to satellites through those radioactive fission products. They will cause problems with communications that try to move through that. So one way around that is just do relays and talk around, to another satellite and relay to the satellite you want to talk to, maybe at a higher orbit. But it does cause problems out in space more than just EMP on the ground. All right, so that is all the effects that you can get out of a nuclear weapon. All right, and I hope you see that they are very destructive weapons, right? They have an awesome power contained inside the atoms of uranium and plutonium that we have learned to harness. However, they're not going to destroy the entire world with a single nuclear weapon, right? It doesn't set the atmosphere on fire, right? A low-yield nuclear weapon used on a battlefield does not end the war, does not stop your mission. You still have to continue your mission. It's very possible that a low-yield 10 kilotons or less nuclear weapon used against for instance, a military battalion, right, is only going to affect a company within that battalion, all right? That battalion doesn't all just go home. They still continue their mission, and that's why it's important to understand these effects. Realize that it's not game over, man. All right? Now, if you're close, you're going to have a very bad day, right? If you're within those blast radius we kind of talked about, right, that's a very bad day. You're going to die more ways than one, and it's not going to be painless, right? However, if you're not immediately killed, it's not as bad as Hollywood would like you to believe. So I'm going to show this video of probably one of the better weapons detonation images from Hollywood until the end. So we'll go ahead and switch to this. You've probably seen this before. Terminator 2, right? Judgment Day, Laura Connor's dream. So we'll go ahead and watch this video. All right, so watching that movie or that clip, you'll probably maybe appreciate a little more how well they did in Hollywood. You saw the bright flash of light, right? You saw everything was on fire, which is a little bit, like the people's skin wouldn't actually catch on fire, but you see the immediate thermal pulse, right? You see the mushroom cloud, and then you see the blast wave coming a little while later. So that timing is really, really good. I'm not sure how big that weapon was that was used, but I think the blast wave traveled a little farther than it actually would. And then you notice like the fact that her younger self with her kid that turned to ash and blew away, and then somehow her skeleton, like all her skin melted away, but her skeleton stayed intact. That's where it gets a little crazy, right? But it's a good appreciation, one of the better nuclear weapon detonations seen in Hollywood. All right, so kind of want to just conclude here with this last point, right? If a low-yield nuclear weapon is used on a battlefield, it's still very possible to fight through that nuclear environment and continue your mission. Everyone is not dead, and it's definitely something you can continue on if you know what to expect and it kind of doesn't catch you off guard. If you have any further questions, you'd like some more information, you can see my email is listed here. Please reach out to me, and we can get you more information or help you if you'd like to include nuclear weapons in your war games. Thank you very much.